So it's my pleasure to introduce Vladimir Albus, Dr. Vladimir Albus, who's co-founder and CTO at NGD Systems, which is based in Irvine. He focuses on developing SoCs that implement intelligent storage technology for data centers and fog computing. And I just paused there to think, fog computing, that's good for the Bay Area because we have a lot of fog here. Anyway, he has developed SoC-based solid-state solutions for more than 10 years, during which time his teams have released many enterprise SSD controllers. Now, before co-founding NGD Systems, again, 2013, he was Senior Director of SoC Development at Western Digital and STEC, which later became part of Western Digital. He's the author of more than 30 scientific publications on subjects such as SoCs, computer architecture, and he's the co-author of more than 20 patents. He earned his PhD in microelectronics from the National Polytechnic Institute of Grenoble, France. Now, not only will Dr. Albus be coming up here, but two other people are going to be coming up. First, we'll hear from Scott Shanley, who's Vice President of Marketing. And we're also later going to hear from Jae-Young Do, who is a researcher at Microsoft and a strategic partner with NGD. So please help me welcome the NGD team. Thank you.
Thank you, Gene. Okay. Well, good morning. Glad to be up, have an opportunity to come up and talk to you guys about some fun things that are going on in storage. So we've heard from Shannon Systems about Open Channel. You've heard a lot of different presentations earlier in the week about different types of flash and technology. We take a look at doing storage a little differently and making it a little smarter for everybody's use case. So we talk about a lot of different things, and at least I personally love to talk about things using examples. So the needle in a haystack is always a very good example to talk to, trying to find something that's very difficult to find. And so what we thought about from this perspective is that's a little overused, and I thought I'd have a little more fun with it. So what if we lost our little girl in a football stadium, and thinking about how we can solve the problem of locating her more quickly when she's sitting in a stadium like this? But this isn't even the problem. This is a well-lit stadium. It's got multiple colors. I don't have any problems. We get to a night game, we have even more problems because we have low light conditions. We don't have the ability to pay close attention. And because I'm from Boise, Idaho, what happens when you go to Blue and Orange Day at night in a stadium and you're looking for a nice lost little girl who's wearing an orange shirt? So security is going to try to do their thing. I'll talk about how they kind of look for it today, and we'll talk about through the rest of the presentation how we help find her. And don't forget, her whole family happens to be enjoying the same color scheme. So the idea here is that we need to have smarter ways to find people or persons or images faster, and we're going to use that concept of image searching as the basis of the rest of the presentation today. So when you're looking for something like that in today's environment, you're going to sit in a surveillance room and you're going to stare at 180 different cameras across 16 screens, and you have 2 sets of eyes. And how do you find that person quickly? We have new, cool, fancy AI algorithms, but at the same time, those have to be able to get access to the data. And when you're streaming 4K in, reading it back out is not as efficient to have to put it into main memory, especially if your CPUs and your memory footprint are not fast enough or powerful enough to be able to do it in the amount of time you're looking for. So if these guys are looking at 180 closed circuit TVs and there's 2 sets of eyes and they find something up in the top right, but they're really looking for something in the bottom left, you're not going to find it fast enough. And this is it's a time problem. We're wasting time looking for something. And in this case of a lost little football fan, it'd be nice to get her back to her parents pretty quickly and not have to worry about doing a manual search of every seat in the stadium. So why is this important? And why is it the kind of the use of the example? We had some friends at Actual Tech Media did a survey of a bunch of IT folks and said, what's your storage bottleneck problem? And they did a survey. They asked, what can we find wrong or what can we find right with the world? And you can see all the usual suspects. Networking gets in the way because we need to go to 100 gig Ethernet. We have storage array controllers that tend to put a little bit of overhead. But we have NVMe. We have PCIe Gen 3 and Gen 4 coming along. So that makes you wonder, why is it that storage still ranked at 46% of the reason why there's a storage bottleneck? And it has to do with the fact that we're treating storage today as somewhat dumb. We're storing data, but we're not doing anything with it on that disk. We're not taking advantage of what that device itself can do. We think we're making the interface faster, but that doesn't move the bits faster. 4 hours to transfer 1 petabyte of data over PCIe Gen 4 at 32 lanes is just not fast enough. So What's causing this problem and the storage bottleneck? It's the data tsunami. We are generating petabytes a day. We are doing different things. You can see from all this, all these articles that we're not the ones with the problem. It's a well-known problem dating well back into one of the articles here is posted in 2008. Another issue we run into, not so much in the US today, but definitely in other countries like EMEA and developing world, it's a power problem. Everything's getting hotter. When I first introduced SSDs with the team at STEC, we had a very low power drive compared to everything else. But with NVMe, we're talking 25, 40 watts a drive. You put 48 of those in a server, you're sucking down gigawatts or all that kind of thing. And you can see here, free cooling. We tried to put stuff out into the nice cold climates, but we're warming those up. Our friends at Microsoft dropped something in the bottom of the ocean to put it closer to their users, but at the same time, it's using cooling and submarine technology to cool it down so they don't have to pay for air conditioning, if you will. And then now the next big thing, and as mentioned, fog computing around here, of course, because of the fog in the Bay Area. But the edge, we have a lot of issues with near data processing because as I generate a lot of data at the edge, I got to move it somewhere to analyze it. And we have really big pipes, but there's always going to be something in the middle. And you'll hear a little bit about that from Vladimir in just a minute. So how do we solve this data and compute problem? We came up with a little technology, and we're happy to say that we won Best of Show award for it last night, and it's called In Situ Processing. It gives us the ability to manage 4 terabytes of data going into an autonomous car per day, and it allows us to help with smart cities and 5G deployments, because 5G is fast, but you still can clog those pipes. So what I want to do now is take the opportunity to get the marketing guy off stage and get back to some more technical deep dive presentations. So I'm going to invite up our CTO, Dr. Vladimir Albus.
So thanks for the introduction. And we all know that data is growing at an enormously fast pace, as Scott said. It's also becoming valuable for businesses and society in general. Data needs to be analyzed, parsed, mined all the time. The data sets are growing enormously. We talk petabyte scale Hadoop clusters. So the increasing overheads of computing-centric architecture, exemplified by the storage to computing bandwidth mismatch, make near data processing an attractive alternative for at least 2 main reasons. One is that moving computation close to data reduces data movement and therefore saves power and optimizes latency. And providing a better matching of computation to data capacity, data bandwidth, and data locality makes for more balanced systems, which are more optimized. On the software side, in the past 10 years, distributed software frameworks such as Hadoop and MapReduce have popularized both the concept of moving computation to data, so a lot of programmers out there that are comfortable with that, but also have honed the skills of programmers that do actually program near data processing hardware. To make it a reality, we need to tackle at least 3 important factors that I'm going to highlight, but maybe more than that, but I'm just going to highlight these 3. So number 1 is power density. That's measured in watts per terabyte. That's a very important metric nowadays. A lot of our customers are focused on that. Second is volumetric density. We need to pack more storage into a much smaller volume, right? And therefore, like smaller form factors are becoming very attractive. And then one of the biggest headaches for all computing systems, data bottlenecks. Right? So we need to tackle at least these 2. So in situ processing is the technology that we have developed to push computation to the storage device itself. In situ processing enables near data processing as well as distributed processing. And the combination of these 2 powerful approaches make it a very interesting architectural solution for data analytics. Within situ processing, we first address the programming model, right? It is imperative to provide developers with a seamless programming model, something that they're very familiar with. Programmers, that's my experience, and I've worked in many companies before, programmers do not adopt platforms that are not easy to program, they're not familiar with. Our intelligent SSDs run on 64-bit Linux OS and are exposed via TCP/IP protocol. So every programmer that we have worked with loves this platform because it's very similar to what they've been using so far. Secondly, it's crucial to manage the data capacity growth in the data center and at the edge. So we've architected our SSDs to provide the highest capacity with 3D TLC and QLC flash. We'll talk a little bit more about it later. Finally, the solution needs to be scalable. It needs to scale with data growth. And it does so simply because of the fact that we are adding computing resources every time we add a storage device to the computing system, right? That's how we scale with data. So before we talk more about what an intelligent SSD is and how we've done it, I would like to explore a little bit some of the dimensions related to the computational storage in general, right? So there's other companies working in the field, but I feel that we all have to work and explore these dimensions. It's important in our view to provide for a sophisticated operating system going forward and go beyond bare metal or simple RTOSes. Next, we need to pick the right hardware infrastructure, forego the 32-bit real-time embedded processor that we all have in our SSDs, and move towards more powerful 64-bit application processors and more programmable hardware solutions. The third dimension is software, right, as it pertains to user application. So we propose that high-level applications should run in storage, and it's possible, and we're doing it. Container-based virtualization that can also run in the drive brings platform independence, isolation, and resource sharing. Containers can also be orchestrated, which is a reality now, for more efficient and scalable deployments of applications where the data resides, in the storage, be it in the data center or at the edge. Finally, near data AI becomes attainable. So we're talking about running AI in the storage where the data resides, and creating many new possibilities for data analytics. And the final touch is that we believe that AI hardware acceleration may be the key to even more powerful computational storage platforms in the near future. And hopefully we'll talk about it next year. So the new platform, the Newport platform that NGD is launching is built around an SSD controller and our custom firmware. So we do it all in-house. The controller is manufactured using a bleeding edge technology, 14-nanometer FinFET process for higher performance and lower power, especially leakage. To our knowledge, it's the first SSD controller that's been designed and manufactured in sub-20-nanometer process. This SoC is powered with 64-bit application ARM processors and dedicated hardware acceleration engines to deliver processing power and best-in-class storage performance. The software stack includes Linux 64-bit OS, such as Ubuntu or any derivative coming from Yocto, and support for Docker containers. We're going to expand to more container technologies out there that are very interesting, especially for the edge. But so far, we've experimented a lot with Docker. This platform enables the porting and development of all sorts of applications, such as TensorFlow, and we have interesting experiment with image classification that we're going to talk about, Facebook AI similarity search, OpenAL PR for license plate recognition, and a lot more. So NGD Systems is delivering the Newport platform in several form factors to provide the largest capacity spectrum, the lowest power density, and the highest volumetric density. We're using 3D TLC and QLC flash to address the needs of customers by providing low power, high capacity, reliable drives at a very low cost. Traditional form factors such as U.2 and add-in card are supported, but we're also supporting the denser and lower power new rack scale form factors such as M.2 and very soon EDSFF. Now, let's take a look at some of the use cases we've been working on with our customers. So distributed software frameworks such as MapReduce and Hadoop are actually, for us, a very low-hanging fruit, since they fundamentally rely on the concept of moving computation to data. So we're just pushing it a little bit further. But we have also experimented with a variety of applications that most likely you've never heard of, that can be inherently parallelized and benefit from in-storage execution. And when I mean that you never heard of running in storage. I'm going to give a few examples in this slide. So we've ported and ran a Dockerized application called OpenALPR that I mentioned previously that can search and match license plates of images that are stored inside the drive without moving data out of the storage. So this is a perfect example of how we can use containers with our technology. We have also used an AI application developed in a partnership with the academia, and we're going to be publishing a paper soon about this, on tracking objects in videos that allows us to track objects in videos that are stored in our drives, either backwards or forwards. That allows it to go back in time. That's very interesting. And another very interesting example is the use of Google's TensorFlow in Septure-V3, for those who are familiar with it, for image classification, running on the drive itself. So that drive can run TensorFlow. So imagine the possibilities then you can offload this type of AI processing on all your storage devices, and they're all potentially running at the same time. Now, we know that the systems are expanding, the number of drives is expanding, so you can harvest all that power. So at this point, you are probably ready to ask about performance, right? Everybody is interested in that. And that's when I'm going to introduce you to our partner, Dr. Jae Young Do, that is a researcher at Microsoft, that has worked with us on a very interesting proof of concept using our technology. We're still in the beginning of our work, but we have some preliminary results that he's going to share with you. Thank you. Jay?
Thank you. So the software-defined control and management has become an inevitable trend that is touching already many parts of the data center infrastructure. So as the most recent example, we can think of programmable intelligent network interfaces that enable deep telemetry or more granular traffic management. We have seen this trend with graphic cards as well. So initially, they were born out of the need of the multimedia applications only, but now they became fully programmable, and the general purpose graphics processing units, GPUs, are heavily being used for machine learning and deep learning tasks. So we believe data center storage interface will be on the same path of evolution. So here I want to show you one conventional and community SSD storage server. So we have a host machine, and there's a bunch of flash SSDs like that. And to connect the flash SSDs to the host machine, we are using a number of PCIe switches like that. So in this architecture, if we need more capacity, it is easy to scale up by putting more SSDs into the server. However, as the number of devices increases, we will have a higher cost of moving data. So what does this mean? So let's do a quick math. So here, I assume that enterprise-level SSD contains about 32 flash channels, and each flash channel can keep up with like a 500 megabytes per second throughput. Then we can think like in a single SSD, the internal bandwidth could be like a 16 gigabytes per second. And since there are 64 flash SSDs in this example, there are going to be 1 terabytes per second as an aggregated internal bandwidth. However, this huge throughput is going to be limited by the host interface speed, which is 16 gigabytes per second in this example. So as you can see in this example, there's a huge throughput gap between the host side and SSD side. And one of the ways of leveraging this huge throughput benefit is to run applications inside SSDs. So actually, about 5 years ago, we explored the opportunities to make the flash SSDs as programmable intelligent devices in the context of analytic queries. So we have a host machine and just regular SSDs, and the data is on the SSDs. To answer a query like that, the very first thing we need to do is load all the data from SSD to host, then execute some operators like a filter or aggregation, and then make the final report to show the result to the user. So what we did was we moved some of the operators and then ran them inside SSDs. And as a result of this, only a fraction of data is needed to be transferred to the host to make the same report to the user. It was sort of okay. I mean, even though we observed some performance improvement, we also encountered a lot of challenges. The first challenge was there's not enough spare processing power to run user programs. So low-performance embedded processors and high cost of random accessing DRAM easily became the performance bottleneck. Another problem was the development environment was not friendly. To run the applications inside the SSD, we had to modify the firmware of the SSD, recompile, and rerun the SSD with a new firmware. To debug the program, we had to use hardware debugging box, which is far primitive than software debugging tool like Visual Studio. Finally, another issue was actually this work was only for the research purpose, so there was no commercially and publicly available programmable SSDs. Fortunately, there have been some changes that help us explore the programming SSDs in a better way. First, resources inside SSDs are getting powerful. Not low-performance embedded processors, but general-purpose multi-core processors with multi-gigabytes of DRAM and some hardware accelerators where we can offload some compute-intensive tasks. More importantly, I think it is getting much, much easier to program SSDs with the trend of moving toward server-like operating system compared to a proprietary firmware-level operating system. This is really important, and this means for the application developers like me, we can keep using the existing tools, libraries, and expertise that allows us to keep focusing on our own work instead of spending tremendous amount of time to getting familiar with the low-level development environment. So with such trends, in addition to the high throughput benefits, we are able to enjoy the much higher compute capabilities like that. And this is why we started a project called SoftFlash at Microsoft Research. The goal of the project is to create a software-defined storage substrate of flash SSDs in the data center. So basically, we want to provide better bridge the gap between the application requirements and the flash memory capabilities to innovate in-house at cloud speed. So currently, we are exploring several value propositions of using such intelligent SSDs. And this is one of the examples I want to show. So I think that all of us are really familiar with what image search is. When image query is given, then the search tool returns a set of images that is similar to the given query image. Like this. So there are many different ways of doing such search, but in order to return the result set as quickly as possible, usually target image data sets have to be maintained in memory, and the search is performed against the in-memory data set. Obviously, this requires a lot of memory space to hold data set. So in our configuration, to hold 10 billion images, we need about 4 terabytes DRAM, which is very huge. So we thought we should be able to provide better solution for this if we had intelligent SSDs. So this is one of the preliminary results I'm going to share with you. So here I'm going to show you how many image queries can be handled per second. So compared to using only host only, by adding more intelligent SSDs, we got 4x throughput improvement. So one thing to note here is that this is only preliminary results, and we haven't considered many different aspects like I/O cost of moving data. So if we consider all the aspects, then we would be able to get higher performance improvement. and more interesting results are coming soon. So please stay tuned. So I want to bring Scott back to the stage to wrap up.
All right, Jay, thank you very much. So 20 minutes isn't a lot of time to be able to drive through a bunch of content, so just leave you with some parting thoughts. We talked about finding a needle in a haystack. So I talked about a lost little girl. We introduced Situ Processing to enable speeding that technology movement up. Bigger pipes feed smaller ones. It doesn't matter how fast it is. There's always going to be a fire hose talking to a garden hose, so just make it so that everything runs at a garden hose speed. You can do that by doing intelligence inside the SSD. Smarter storage does work. It works really well when you have someone able to show actual real-world results for you as well, so we appreciate our friends from Microsoft participating today with us and showing you guys what can really be done with computational storage products. And when you do it, you need to do it right. We did, as Vladimir mentioned, we had to do a custom ASIC to be able to get the products and the capabilities that are really needed to propel this technology forward. There are a lot of platform opportunities that you can use to do that, but nothing fits in the form factors of today without going into some form of an ASIC-based hardened controller. And of course, power, power, power. We also made sure to focus heavily on the ability to give a very low power solution with a very high computational power use case. So thank you guys very much for your time today. If you have any questions and would like to talk to us, we'll be available after the event, and the show floor is open for a little while longer. We've got a booth in there as well. So appreciate your time, and thank you very much.